let's continue to the discussion about uniform plane wave. In the previous lecture, we defined that the vector phase constant beta is the result of the negative of the gradient of phase function phi, and it's by definition is the direction beta hat, that is the unit vector of beta, is the direction in parallel with the direction of maximum change of phase 相位变动最大的方向，相位变动最大的方向。And the speed, so it's also referred as the phase velocity, 像速度 phase velocity. And in our previous discussion, we know that the projection of the phase velocity v are all greater than the phase velocity along the propagation direction. 所以像速度可以轻易超越波传播的速度像速度的投影像速度的投影你用 v 等于 this is the definition of the phase velocity omega over beta, but the projection, 所以有的时候你可以写成 Vp 指的是像速度 phase velocity, but the projection of this over any direction are greater or at least equal to Vp, so you can surpass the 3 times 10 to the 8th limit very easily. However, if you want to deliver information or deliver energy through that wave, the eventual effective velocity of the information, the velocity of the energy, cannot surpass the speed of light, cannot surpass 3 times 8 to the 10 to the 8th. Taking example, have you performed wireless communication in light speed? Well, the Homo sapien, the human race, have been using light to communicate for eons, for millions of years, okay? You wave your hands. This is a form of communication in terms of light, right? You see my hands immediately. But you don't know if I'm welcoming you by waving my hands, or if I am asking for your help by waving my hands. It takes about a second or two to understand what I'm talking about. So that's the information, right? You see me waving hands immediately, but it takes seconds to understand or to demodulate the modulated information, the modulated signal, right? So there is nothing like hyper optic, hyper speed. So you cannot communicate or you cannot deliver energy with a speed faster than light, right? So the actual energy propagation speed, or the communication, the speed of the communication over the modulated signal, is referred as the group velocity that we should discuss later in today's lecture, right? So this is the wave propagation direction. This is wave propagation description for the wave propagation direction. So if the direction of your choice is in parallel with the wave propagation direction, then the speed of this can be derived with these equations. Again, you're taking the a spatial and time derivative on both sides, and you end up with this Vp. That's the phase velocity, which is the smallest number. The smallest phase velocity that you can have is the smallest possible velocity you can have for phase velocity because it's along the wave propagating direction, along the gradient of phi, so that you can have the maximum rate of change. So because the divider is the largest number possible, so the phase velocity is the smallest number possible, right? So next, let's talk about TEM wave. So it's a special case for uniform plane wave. It's kind of a special case for the. So what is TEM wave? The full name is transverse electromagnetic wave. That is, the electrical field intensity, the electrical field, magnetic field, and the wave propagation vector are perpendicular to each other. 电场方向、磁场方向还有波形镜方向两两正交。So a TEM mode is one whose field intensity E and H contained in a local equal phase plane that is independent of time and perpendicular to the direction of propagation at any time. So 电场方向、磁场方向，还有波的行进方向，看你要用 K 还是用贝塔都可以啊，两两正交啊。然后事实上它有一个比较好玩的哈，我们先简单写啦，但是之后我们会写比较正式的写法啊。也就是 the cross product of E and H, not the order matters 啊 ，the order matters， 这顺序是重要的。E cross H， 它的新的向量会跟 K 是平行的啊。然后那它有一个 A、B、C 三个向量外积的轮转特性嘛，哈。所以假如是 H cross K 的话，出来的方向是跟电场同方向；K cross E 的话，出来是跟磁场同方向。因为它们 because they are perpendicular to each other, so you have this kind of property. So in plane waves, equal phase surface are parallel planar surface, and uniform plane wave equal phase surfaces are also equal amplitude surfaces. And as you can see in this graph, for any equal phase plane, the E and H field lies along the plane. 电场跟磁场嘛，有没有注意到这个图哈？它这边所要显示的一个目的是说电场方向跟磁场方向是落在平面上，然后它们正交于平面的传播方向、行进方向啊。因为 by definition they are perpendicular to each other. So because E and H field must be perpendicular to the propagation direction, the direction of the surface. So E and H field must lies in the on the equal phase plane. What is the importance of TEM wave? ？TM wave 的重要在于哪里？ This is the TM wave is the only form of propagating wave in free space. TM wave is the only propagating form of wave in unbounded region. 更准确来讲是 unbounded region. 那 free space 是 unbounded region， 所以 free space 里头能够跑的不一定是 TEM wave。Okay, so TEM wave is the only form that can propagate distance in free space. Of course, some of you might heard of the so-called TM wave, TE wave, TE mode, TM mode. I bet you are students of Professor Ma, Professor 曾老，这边有没有曾老师？有没有曾道雄老师的学生？没有。有没有王昌荣的学生？有吗？马老师的学生应该有吧？OK， 好。所以，假如你有做那个微波电路的话，so if you are working on transmission line design, microwave circuit engineering, you might come across to certain type of transmission lines that is not that the wave propagating in it is not in TM mode. But usually, most of the transmission line propagates using TM wave, TM mode. Okay, can you give me some example? Can you think of some transmission line type that the wave going within it is propagating using the TM wave mode? Coaxial cable。Coaxial cable 里头跑的是 TM wave， microstrip line 是不是？microstrip line 也是coplanar waveguide ，yeah. Or can you think of something that is not propagating in TM wave mode? Waveguide, yeah, waveguide. What difference between TM wave mode, type of transmission line, is non-TM wave type? 它们两个分别在哪里？Well, for waveguides, you have the so-called cutoff frequency, right? The most beautiful thing about transmission lines that propagates along TEM wave with TM wave is the phase velocity of all frequencies are the same. Theoretically speaking. 光速多少？3乘以10的8次方嘛。可见光也是3乘以10的8次方，微波也是3乘以10的8次方。所以你只要是用 TEM wave 的方式，在 unbounded region 里头方式传播的话，你的光速传播的速度都是一样的，任何频率都是一样的。for TEM wave。所以你在 coaxial cable 里头，你的那个速度是什么？你的光速是什么？是吗？我有写错吗？对了，对，应该没错。只要你是 if you are talking about wave velocity in the coaxial cable, well, need to take into account the permittivity of the material. But you don't have to worry about the dependence on frequency, right? All waves of all frequency all propagates with the same speed. So you don't have the problem of dispersion. Dispersion, have you ever heard of that? Dispersion, 中文叫色散，意思说那个波垮掉了。因为不同频率的波跑不一样的速度，然后那个讯号就会垮掉。那这个现象我们称之为色散 （dispersion）。Right? So the nice thing about TEM wave is wave of all frequencies all goes at the same speed. On the other hand, if you have non-TEM wave, such as the wave in the rectangular waveguide, circular waveguide, you may come into a problem that is wave of different phase frequencies propagate with different velocity. Why? 为什么会这样？假如你是 TEM wave 的话，你在 free space 传事实上你就是走直线。For TEM wave propagating in free space, we're just propagating along the direction because there are no boundaries, there are no obstacles to block your path. So just going on and on and on. On the other hand, if you have a waveguide, your propagation region is bounded. So you are kind of bouncing back and forth within the waveguide. So your actual speed, even though at this point the speed of wave is the same as, let's say, equal to c as well. But because you are bouncing back and forth, so your effective propagating velocity is smaller than speed of light. And this is getting worse when the frequency approaches to the so-called cutoff frequency. What happens at the cutoff frequency? I mean, if you have a wave of higher frequency means smaller wavelengths. So if you are saying if you have force WR 叫那个 WR430的 waveguide， 这个频率是哪一个？有没有人知道？我看一下，德先生啊，430是哪个频率？不记得了。好，6G 哦 ，OK 好，是吗？啊，就是只要6G 啊 ，OK 好。假如是6G 好了，假设6G 啊，6G 的波长是多少？5公分啊，所以那个 waveguide 的那个高度的间距哈，假如你是6G cutoff frequency 是6G 的话，你的那个高度是1/2个 lambda at the cutoff frequency， 所以大概是3公分呢。OK， 啊 ，because the wavelength of 6 GHz is 5 centimeter, I'm sorry. Then the height of the waveguide is about half wavelength of the cutoff frequency. So say 2.5 centimeter. So if you have a signal of 60 gigahertz, what is the wavelength of 60 gigahertz? 5 millimeter. So you had a very short wavelength. So this waveguide of a height of 25 millimeter is very large for your 60 gigahertz signal. So it seems to the 60 gigahertz signal that the waveguide is not there. Okay, it's kind of propagating in the free space. So the speed of propagation for a very high frequency approaches to speed of light. On the other hand, if you have a low frequency signal, say 6 gigahertz, the boundary the top and bottom plate of the waveguide is layered because of your large wavelength. So actually, it's getting very difficult to signal right about 6 gigahertz. As to the for the 6 gigahertz signal, the wavelength is too big for the waveguide. So it's actually, it still propagates, but it's bouncing back and forth very quickly within the waveguide. So its speed will approaches to 0 when when the frequency approaches to the cutoff frequency. So if you have a frequency, if you have a signal of 3 gigahertz, it cannot get into this waveguide. Okay, no room for that, right? Okay, so okay, go back to the slides. The good thing about TEM wave is there is no dispersion phenomenon in theory. Of course, for actual implementation of, so the transmission line types such as microstrip line, coplanar waveguide, and coaxial waveguide, as long as the E and H field within the transmission line is perpendicular to the direction of the line, they are supposed to propagate in the TEM wave mode. And you experience no dispersion. But in actual implementation, you do have dispersion effect in coaxial cable, in microstrip line on the substrate. Why? 实际上，即便是同轴缆线或者是微带这些线，这些理论上它是用 TEM 模式在跑的电磁波，它还是有色散的现象。为什么嘞？ Material property. Because most transmission lines are filled with dielectric. The dielectric, the probability, the dielectric constant of the dielectrics of the substrate is supposed to be a constant, but it's not, right? No, it's very slowly as the frequency change. Okay, so as long as the line is short, as long as the signal that you are interested in is not a very broadband, ultra wideband signal, you should be safe. You should be free from the dispersion phenomenon. On the other hand, if you have a very broadband signal or you have a very long line, very long transmission line, then the dispersion phenomenon will kick in eventually. 也是材料的那个介链系数，它并不是真的是一个 constant， 所以只要频率变动范围够大的话，那个 permittivity 不是 constant， 所以不同频率的讯号就会有不同的传播速度，那个传播速度还是会造成色散，不过一般我们在实验室里头用的那些 coaxial cable 或者你做电路的那个线，大概不用去考虑色散的原因，原因是你的线不长，或者说你的有兴趣的那个讯号的频宽没那么大，那所以在大多数的状况底下，还是可以假设并没有色散的现象。Okay. Okay, so let's go back to the discussion about TEM wave. So this is the Gauss's law of electrical field. That is, the divergence of electrical field equals to 0 in a source-free region. So the actual Maxwell equation for Gauss's law of electrical field is the divergence of E, not divergence of D equal to charge density, or divergence of E equals to charge density over permittivity. Okay, and So for a source-free region in cylindrical coordinate system, the wave equation with respect to electrical field is this. Then the general formation for the electrical field intensity in cylindrical in Cartesian coordinate system is this. E can be divided into its projection on x, y, and z directions. So for the projection in any one of the three directions, you can write wave equation in this form. So the wave can be separated into three axes. Again, you can substitute the general wave equation, that is the amplitude part and the phase function part, amplitude function and the phase function. And the phase constant beta, the vector phase constant beta, can be separated into the three products of its projection along the x, y, and z directions. But overall speaking, the square of beta equals to omega to the square times mu times epsilon. Again, this is true for lossless medium. 在 lossless case 才成立哦。So according to this expression, you can write the phase function like this. Of course, the phase function, the equal phase fronts can be pointing toward any directions, according to bx, by, and bz. 等下位面当然可以朝任意的方向。但这些结果其实在我们前面其实都已经有看过了，都已经有看过了。So by defining the vector phase constant beta as a vector of its projection, synthesized with its projection along x, y, and z direction, that is bs, by, and bz, the E field can be expressed like this. So this is a uniform plane wave, uniform plane wave in terms of electrical field. So the amplitude function is E sub 0, and the phase function is minus beta r, the dot product of beta and position vector r. OK， 可以写作这个形式啊，所以这张其实还是算复习了。当然了，假如说你电磁波、电磁学1、2已经忘得差不多了，那看起来有点比较像新的了，但不然的话还是复习了，我们把波的那个形式再复习一次。All right. So to satisfy the wave function, that is the Laplacian plus beta to the square of E equal to 0, you have two conditions need to be satisfied for this expression to be valid. That is, beta dot beta equal to beta square, and the divergence of E equal to 0, which is the condition for sourceless. Sourceless. Not that the first term here is what? Laplacian of vector E. Okay? I forgot to mention that on top of curl operation, divergence operation on vector, and gradient operator on scalar, we have Laplacian of vector, and we also have Laplacian of scalar. Okay? Laplacian of scalar is easy. It's taking the spatial derivative of phi along x direction twice, along y direction twice, along the z direction twice, while the Laplacian of vector is more complicated. So, where's my vector identity? Where's my vector identity? Well, to do this, you need to check out the vector identity, okay? Is this the same? No. It's actually more complicated than that. This is just one component of the Laplacian of a vector. It actually comes with other terms, but I don't. But I don't know how to write them. I forgot them. But anyway, with some help of vector identity and terminologies, you end up with this. 我跟各位提醒一下哦。The curl of any vector of vector E is not the Laplacian of E. Laplacian 有分向量的 Laplacian 跟存量的 Laplacian。向量的 Laplacian 至少有2项啊。可是那个，假如你用用一些带入一些 vector identity 的那些技巧的话，你可以把它简化啊。那可以简化成像这个样子啊，但它不是哦，它不是Laplacian of E哦，但它其他项会被消掉了哦，在无缘的这个状况底下啊，不过没关系，我们先拿第3章的结果哈。So from chapter 3 you have the two, so you need to go back to chapter 3 to check up with the Laplacian of the vector. Okay. So under the condition of source-free condition, we can use the result from chapter 3, that is the curl of E minus beta to the square of E equals to 0. That will be the things that you need to resolve. So taking the divergence on both sides, that is the divergence operator. Here we're taking the divergence of E inside, and the divergence of 0 is 0, of course. And now we use another vector identity, that is the divergence of the curl of any vector must equal to 0. So therefore, the first term goes to 0. The first term goes to 0. So you end up with this result. That is, the divergence of E must equal to 0. This is kind of like a Möbius loop or something like that. 蛋生鸡，鸡生蛋，然后你推了半天之后，你回到的结果就是 divergence of E 等于0了。但是 divergence of E 等于0是你的一开始的那个 source-free region condition 啊，对不对？好吧，所以这个证明其实有点那个了哈。Okay, so wave equation can be satisfied in a source-free region. Okay, that's a given. All right, then if we're actually taking the divergence of E within the uniform plane wave representation. So this is your uniform plane wave representation. The magnitude is E sub 0. The phase function is minus beta dot r. So if you're taking the divergence of this, you are taking the divergence of the first term plus the divergence of the second term. However, because the second term is not a vector, so it becomes gradient of this, okay? And the first term goes to 0. Why? Because you have a uniform plane wave. Uniform plane wave. The amplitude is uniform along the no, I'm sorry. The amplitude is a constant as you propagate. along the propagating direction. So you have no magnitude difference. So this thing ends up as 0. So you have a second term only. So if you are taking the gradient of the exponential to the minus j beta r, you end up with minus j beta exponential minus j beta r. So you end up with E dot beta times minus j exponential minus j beta r. Again, this is 0. Why? TEM wave. The propagating direction is perpendicular to the E field and H field as well. So the inner product, the dot product of the two goes to 0. Or, I'm sorry, I'm taking the result as cos. 我把因果搞错了哈，注意哦，我再讲一次。到了这一步以后哈，你可以把它拆解成电场跟传播方向的内积乘上这一项，后面这项你不知道它不等于0。但是我们一开始前提啦哈 ，source free region the divergence of E equals to 0. So we must goes to 0 in this result. So the only thing that can be satisfied for this condition is the dot product of the two equals to 0, which suggests the field direction and the wave propagating direction must be orthogonal, must be perpendicular. 啊，有没有？我刚才有点倒因为果了啊，这样讲才对了啊。因为原来的前提是在 source free region 的时候，电场的 divergence 必定为0。那我们把电场的表示式带进去，然后到这边的时候，你发现要让这个式子等于0要满足等于0的要求，就是前面这个等于0。所以它们传播方向跟电场方向的内积必定为0，也就是它们必定正交啊。So this suggests the electrical field and the direction of propagation must be perpendicular for TM wave. Okay, and if you do the substitute E and beta within this dot product, you can see that beta x times E0x plus beta y times E0y plus beta z times E0z equals to 0. And the next thing is 第二条式子是什么东西？这一条安培电路定律啊。This is the result of Ampere's circuitial law in differential form, in phasor form. Okay? So originally, this is curl of E equals to minus of time derivative. 有没有 minus？ 有没有 minus？ 好像没有。有了。Negative of this. Okay? 但是假如你用phasor form的话，就变成是那 B 你又可以把它代换成 mu h。Okay, so we know this is true. So we substitute the left-hand side of E with TM wave representation, E sub 0 exponential minus j beta r. Then the curl operator of this, which can be divided in two terms, curl of E and the gradient of this cross product with E. And again, because E sub 0 is a constant for TEM wave, so this part goes to 0. So we have the second part remaining. Gradient of exponential minus j beta dot r times E sub 0. And you can actually perform the gradient of this to end up with minus j beta exponential minus j beta dot r cross E sub 0. And because this is a scalar number, so you can place it, you change its position to here. And then the two can be combined as the description of E, of electrical field. Then you end up with this equation, curl of E equals to minus j beta cross E. OK， 这边回去自己看啊，好不好？啊，就是说这边的推导，老师上课讲时间有限，都会比较感觉都会比较快啊，所以你在课堂上的时候只能稍微 follow 啊，只能稍微 follow， 但是你回去自己要想一下，要自己验证一下，好不好？啊。So here is our result, but we're starting with this Maxwell equation relationship. So if you combine this equation with this, you end up with this representation. That is, the magnetic field intensity can be expressed as minus j beta cross E over minus j omega mu. Then you're taking out minus j part, you end up with omega mu, beta cross E over omega mu. You can rewrite the vector beta as the unit vector beta hat times the magnitude of beta like this. And you can identify these three terms as eta. Anyone remember the definition of eta? What is eta? Eta 是什么？本质阻抗啊，本身，叫什么 ？Intrinsic impedance。最简单的 definition 是这一个了啊 ，It's defined as the square root of mu over epsilon. And OK， 不用再推了，在这里 OK。eta 的定义是 mu over epsilon 的 square root 了啊。那你假如把那个贝塔的跟 omega 的定义带进去的话，贝塔is the product of omega times square root of E mu times epsilon. Omega here, mu over here. We massage the equation a little bit. We end up with 1 over eta. OK? 还好不用在黑板上自己推导啊，不然温系啊。OK 好。Okay, so that's the unit vector definition for unit vector. Okay. So if you substitute this with 1 over eta, you end up with a more formal expression for the relationship of E and H field. The H field can be found by taking the unit vector of the propagation direction cross E field divided by eta. Anyone remember what is the definition or what is the implication of eta? Eta 的意义是什么？ eta 的意义是什么？电场跟磁场的比值，对不对？那从这个式子你就可以看到嘛，对不对 ？Beta hat 是 unit vector， 所以它的大小是1嘛。The magnitude of beta hat equals to 1. So eta is E over H. So eta is the ratio. The intrinsic impedance is not a real intrinsic impedance in general or in lossless medium is a real number. So the unit is the same as resistance. But I would suggest you not to remember it as a resistance. You need to remember, you need to know it as the ratio of E field over H field. So in free space, the intrinsic impedance simply represents the ratio of the magnitude of E field over H field. 它就是本质阻抗其实就是电场跟磁场的比值了。在 free space 里头，电场比磁场大377倍嘛，120拍嘛。Okay, so the result of this slide suggests that the magnetic field intensity as well as the direction can be found by wave propagating direction and the electrical field intensity description. And also, if you know only the magnetic field intensity and the propagating direction beta, and you don't know about the electrical field intensity, you can have that by taking this product. Okay? So 两者只要知道，三者只要知道其中两者，那第三者一定会被知道，对不对？So for example, if you're taking eta of eta beta cross H, and you substitute H with beta cross E over eta, then you end up with beta cross E. And by using this vector identity, so again, you use the vector identity over here, and identify as A equal to beta hat, A, B equal to beta hat, C is E. And you don't know with this. This equals to 0 because what? TEM wave. So the two are perpendicular, so it goes to 0. This goes to 1 because you have two univector taking the dot product. So this goes to 1. So you end up with this, minus E. So eta times beta cross H equal to minus E. So E is the minus of eta times beta cross H. And more convenient way is, you know that for cross product, you reverse the order of the cross product, you end up with a minus sign. So you can have this. E equals to eta times H cross beta. 所以下面两个是比较有用的结果，好不好？电场可以有本质阻抗乘上行进方向跟磁场的外积磁场跟行进方向的外积了那磁场等于行进方向跟电场的外积除上eta。All right, so the next topic we'd like to discuss is phase velocity and groove velocity. Okay. So we already discussed the phase velocity, that is the change of rate of phase. So by definition, it's the omega over the gradient of phi, the phase function, which end up as the beta, the number beta, the phase constant. So the velocity of light, the velocity of electromagnetic wave is usually defined in this, omega over beta, as we know. And it equals to 1 over square root of mu times epsilon. And if the wave is propagating in free space, then mu r and epsilon r are all equal to 1. mu 0等于多少？ epsilon 0等于多少？ 8.854乘以10的负12次方跟400乘以10的负7次方嘛，对不对？不记得正常啦，但是上完这一门课要记得不记得是正常啊，但你记得就表示你有在认真在算题目认真算久了就会记得了OK，教书教我刚第1年教也忘记了，教10几年就会记得了。Okay, so speed of light is defined in terms of phase velocity. And here we will introduce another term, that is the group velocity. What is the physical interpretation of group velocity? Group velocity 的物理意涵是什么？从这一句话来看的话，它就是 speed of energy。Speed of energy， 能量传播的速度。能量传播的速度跟相位传播的速度会一样吗？假如是 free space 的话是一样的。那假如说你在材质中传播的话，到后来有可能会不一样。有可能会不一样。Okay, so here's the Poynting vector as we learn from the undergraduate electromagnetic, the Poynting vector is defined as the cross product of E and H field. And here we are talking about time average Poynting vector. Time average Poynting vector. On the basis of we know that the E and H field belongs to sinusoidal signal. 同意吗？这边我们写出来的是时间平均的 Poynting vector， 而我们这边在讨论的是正弦性，特定频率的正弦波讯号，你才可以这样写你能够这样写的原因是因为我没有明显写出来但是我们在讨论的是特定频率的正弦讯号。So for a signal for a sinusoidal signal. For the E and H field of a sinusoidal signal, the time average Poynting vector can be written as 1/2 times E cross H conjugate. Okay, E and H field are of course complex number. And by taking the conjugate, you are kind of getting the real part effectively. So if you substitute the H as E over eta, you know that the unit vector, the conjugate of the unit vector is the unit vector itself. The conjugate of the intrinsic impedance is the complex conjugate of the intrinsic impedance. If intrinsic impedance is a real number, then it's the same. If the intrinsic impedance is a complex number, of course, different. And here you have the cross product twice. So again, you need to resort to the help of vector identity and substitute those terms in here. Even though you have two terms here, by knowing that we are talking about TM wave, the second goes to 0 because E field is perpendicular to the propagating direction. So you end up with this. 1/2 times 1/eta times E dot E conjugate. So effectively you are extracting the amplitude of E to the square. Okay, E sub 0 to the square. And note that this is a vector. 有没有注意到这是一个向量它的是哪个方向？ theta 的方向。所以 Poynting vector 告诉你的是能量传播的方向能量传播的量以及能量传播的方向。Okay, so the time average Poynting vector tells you the direction of energy propagation as well as the amount of energy propagation, amount of moving energy. So the time averaging of this is effective like this. Okay? Taking the real part of S, you will end up with this. 所以代表能量流动的大小与方向。Okay, so now we can discuss under what condition that the group velocity, the velocity of energy, shall equals to the velocity of propagation. Well, there is no direct relation, direct linkage between the two, but I would say that under the condition of lossless medium, the two should be the same. On the other hand, if this is a lossy medium, you may encounter this problem. So the two are not the same. All right. So here is a more general expression for the phase, for the TEM wave, TFM wave expression. Okay. So this is a more general expression of E field. As you can see, it has a constant magnitude of E sub 0. The phase function is here, beta sub j beta sub 0 x cosine phi plus y sine phi. So this is a wave propagating. The propagating direction is along the xy plane. So the phase function is this. 注意在这个例子里头的电场，从电场你可以看电场的描述，可以看得出来，它的波是在 xy 平面上传的。电场的振动方向在哪里 ？What is the direction of E field? Z direction. Okay? So the E field is vibrating along the Z direction, and this is the beta is the propagating direction. What is the direction of H field? E 磁场的方向在哪边 ？E H beta 所以 E cross H 得到 beta， 所以你要得到 H 是什么 ？beta cross E， 可以吧？右手拿出来所以 E 是这个方向嘛 ，beta cross E， 对，这个方向，所以磁场振动方向是可以找得到的。所以说传播方向 beta， OK， minus beta sub 0 cosine phi x minus beta sub 0 sine phi ay. And again, we can verify that the inner product, the dot product of E sub 0 and beta equals to 0. You can, from previous result, you can find the magnetic field direction and the amplitude as well using beta cross E over eta sub 0. Okay, so here is the magnetic field representation, giving the electrical field representation. 所以它的基本波的那个基本参数就可以用刚刚这个例子来去做计算。Okay. Then we try to derive the phase velocity along x, y, and z direction. We know that this is a kind of a wave propagating in free space, because here we have mu sub 0, epsilon sub 0. So it suggests that we are having a wave propagating in free space. Then the speed of light, the phase velocity shall equals to c, that is the speed of light in free space. And we can find out the phase velocity, projection of phase velocity along x, y, and z axis. here we have beta equals to okay, the projection of beta along the z direction is 0. So, by definition, the projection of the wave propagation speed along the x direction Vs equals to omega over beta x. That is this. And as you know, cosine phi is a number between 0 and 1, so this is a number greater than c. So its projection along the x direction is greater than the phase velocity of itself, c. And the same applies to Vy. It's a number greater than c. And its projection along the z-axis is infinity, because beta z equals to 0 along the z direction. So again, you can use this graph to see that the distance along the projected direction is greater than the distance, the shortest distance from one wavefront to the other. 那个蓝色的投影的那个大小，投影的距离大小都比最短距离 d 0还要来得大，所以它的像素度在投影的像素度都会比原来的像素度还要来得大。Okay. So group velocity. Okay, so here is the definition of the group velocity. Group velocity is defined as the Poynting vector divided by time average, total time average energy density. 所以我们在前2页有算过那个 Poynting vector time average 的 Poynting vector 了哈，所以分子的部分是 Poynting vector 的时间平均，而你要除掉的那个分母是，因为 Poynting vector time average Poynting vector have direction and amplitude as well. So with this definition, you can get rid of the amplitude part and have the velocity part only. So the denominator must be the total time average energy density. So its unit is Joule, J over m to the cube, m to the cube. So the unit will become distance over time, velocity 时间，距离除上时间嘛，距离除上时间，好吧？所以其实就是那个 Poynting vector 把它那个能量的大小除掉就是了，能量大小除掉。Okay, the important part is the implication of this result. Though projected phase velocity are larger than speed of light, only group velocity, which equals to the speed or smaller than speed of light, can carry energy and information. So as long as we applied information onto the electromagnetic wave, the effective propagating speed of the energy and the information is equal to or smaller than the speed of light. Energy in space is stored in E and H field. So here is another perspective to examine the wave. Okay, the wave can deliver information, but the wave itself carries energy. 同意吗？电磁波本体是带着能量的。带能量往前传播的，所以有电磁波的存在，就有在空间中传播的能量，同意吗？然后我先讲结论好了，电磁波在传播的时候，它的能量 一半是以电场的形式储存，一半是以磁场的形式储存，不会多不会少，就说你知道电磁波在传播的时候，在空间的分布是长什么样子吗？不是那种什么快打旋风里头打出去的那个光波束还是什么龟派气功对。能量的分布不是这样一条的你今天打一个电磁波能量出来的时候，它实际上不是一条 homogeneous 的那个能量它是这样子一步一步的对。电磁波能量在传的时候不是均匀的，瞬间看到的那个能量分布是长这样子，一坨一坨的有的地方大，有的地方小最大跟零点，OK。那只是说这边的能量一半是电场一半是磁场一半是以电场形式，一半是磁场形式。Okay, so see here is the time average Poynting vector as we have derived in the previous slide. It's propagating in the beta direction, the wave propagating direction, and the magnitude is e sub 0 to the square times over 2 and eta sub 0, the intrinsic impedance. So the time average power density WAV is can be divided into two parts. That is, the time average power density stored in terms of E field and H field. Okay, so you see the subscript as E and H. So the energy stored in terms of electrical field is 1/4 times epsilon e to the square, and the component stored in H field is 1/4 times mu times H to the square. Okay, but because the two are the same, the amount of energy stored in E and H field are the same. So the summation of the two terms will become 1/2 times epsilon sub 0 times e to the square. So the energy velocity, which is defined as the division of time average Poynting vector over the time average power density, is this. And it happens to be the same as the speed of light. Okay, in general, the group velocity should be the same as wave propagating velocity, the smallest phase velocity. 最小的全速度group velocity 会等于最小的相速度。Okay, and the next thing I'd like to examine here is wave impedance. 波的阻抗波的阻抗是不是电阻？不是啦波的阻抗是你的电压电场磁场比值。Okay, so wave impedance should not be interpreted as real resistance, even though the unit is ohm. It should be by definition, it is the ratio of E field over H field. The intrinsic impedance is for uniform plane wave along its propagating direction. The wave impedance here is its projection. along a specific direction. So you can define the wave impedance along positive x direction. And you can also define the wave impedance along negative x direction. So that will be, for the positive x direction, that will be EY over HZ, Y. Y cross Z equal to positive x. On the other hand, Z cross Y, positive Z cross positive Y give you negative x. Okay? So you need to be careful in picking up the components. And you see from the first equation that EY over HZ will give you ZX in the positive direction. The minus of EZ over HY will also give you the wave impedance along the positive x direction. Okay? And this is for arbitrary direction. For total E over total H. Total E over total H. 所以所谓的那个 wave impedance 它就是本质阻抗在特定方向上面的投影量投影量。Okay, so for this expression, okay, for this, so what we do, because the wave impedance is the E and H field ratio projected on a particular direction, for example, in the positive x direction, we found that it equals to eta sub 0 over cosine phi. Phi is the propagation direction on the SY plane, the angle of the propagation direction on the SY plane. So as you can see here, because cosine phi is a number smaller than 1, so you will end up with impedance greater than eta sub 0. Okay? You will end up with impedance greater than eta sub 0. 所以因为是投影的关系，所以它会比那个来的大。那在 y 方向的投影也一样，它也是一样比eta还要来的大。OK。所以大小这件事情要稍微留意一下。OK。好，那我们要看的最后一件事情是 standing wave ratio 今天我们要看的最后一个东西 standing wave ratio. Of course, you heard it in your undergraduate electromagnetic. If you have if you had the microwave engineering or the transmission line study, you have studied the transmission line stuff, you know standing wave ratio. So what is the definition of standing wave ratio? The part of the energy bouncing back and forth over the total energy on the line. OK， 好了，我是随便讲的OK， 大致理解这样。那我们这边可以来看它比较确切的定义了So to have standing wave, you must have positive direction going wave and negative direction going wave. Okay, which means the E field representation of the wave has two components. For example, in this example, you have wave propagating along the z direction, right? You have exponential minus j beta sub z. So actually, the first term represents the wave that going into the positive z direction, 往正逆方向传的成分，对吧？ But the second term represents the wave, the energy going toward the minus z direction. Okay? So standing wave ratio is kind of evaluating the amount of energy going forward and going backward. If there's no energy going backward, that in general is the case you want. Okay, you want all the electromagnetic energy going forward and don't go back. All right, that's the ideal condition. Okay, but in transmission line, in microwave circuits, from time to time you have energy going backward, and they may cause problem. Okay. All right. So if you divide the exponential minus j beta z into two parts, the real part and imaginary part, as you know, you can be divided into cosine beta z plus j sine beta z. So if you do the substitution for exponential minus j beta z and j beta z with cosine beta z plus and minus j sine beta z, you end up with this equation. And because this is expressed in real part and imaginary part, so the magnitude of Ex is this. And the phase of this is more complicated like this. You don't have to memorize that, just knowing the form of this. And as you can see here, total E field is the persistence of Z. So the energy is not distributed evenly in space. Okay? Some places you have larger amount of energy, larger amount of E field, total E field. At a certain point, you have smaller total E field. Then the definition of standing wave ratio is the maximum of total E field over minimum of total E field. So when can you have a maximum of total E field? That is E plus and E minus are in phase. That is cosine 2 pi z equals to 1. Cosine 2 pi 0 equals to 1. But cosine 2 beta z equals to 1. That is beta sub z 0 z equals to m pi. Then this is 1. Then you can have the maximum value of that. That will be sub 0 plus the magnitude of E sub 0 plus the magnitude of E sub 0 minus. Okay. And on the other hand, if this component is half pi or minus positive and negative half pi, then you end up with a smallest number, minus 1, the smallest number. So the minimum will be this. And as I said before, the standing wave ratio definition of the maximum total E field over the minimum of total E field. So it's like this. And this can be massaged as this. Okay. 1 plus E minus over E plus divided by E1 minus E minus over E plus. And you should be able to identify that this is the so-called reflection coefficient in terms of E field. 电场的反射系数嘛，电场的反射系数。So the reflection coefficient of V field is gamma. Okay, it's gamma. So standing wave ratio is defined as 1 plus magnitude of gamma divided by 1 minus magnitude of gamma. Okay. So in ideal case, SWR equals to what? 理想上 SWR 应该等于多少? What is the ideal condition for transmission line? Total transmission, no reflection. That is, reflection coefficient equals to 0. So if the reflection coefficient equals to 0, SWR equals to 1. What is the worst case? The worst case is reflected field intensity is the same as incident field intensity. That is, the reflection coefficient is 1. Not necessarily 1. The amplitude of the reflection coefficient equals to 1 because the reflected field can come with a phase change. Okay, the phase change does not matter the magnitude of the reflection coefficient. Okay, so as long as the magnitude of the reflection coefficient is 1, then you end up with a standing wave ratio of infinity. So the SWR equal to infinity is the worst case. All right. Okay, so that's about it for today's lecture. So next week we will continue with wave in low C medium. Okay. So please hang out your previous homeworks, and next Monday you should give me the homework for the first part of chapter 4.